Good morning, everyone. I hope everyone is very well caffeinated for this wild ride. This is a project that Emma already mentioned yesterday. This is what we've been working on for the past 18 months, so we're slightly past halfway there. What we're going to talk about today is the hygromechanical response of mostly cellulose acetate films, but a little bit of polyurethane foams, due to something that has been a priority at IPI for a very long time, which is dynamic environmental management. So how we're going to go about this presentation is essentially go through this very lengthy title from the end till the beginning. So we start with the dynamic environmental management, and what it is essentially trying to make sure that the objects are safe, but the environment is allowed to fluctuate enough for make substantial savings in terms of environmental and monetary cost. And this is because there is a growing pressure on the cultural heritage and collecting institutions to make those savings, to lower their impact, and changes in environmental management are a thing that allows those institutions to reduce those costs and to make those savings in a very quick and a very effective way, and can be one of the most effective tools to do it. So here you have an example from SF MoMA, who's been doing this for years, and basically what you see here are environmental RH set points that fluctuate throughout the year according to the seasons. And the truth is that most of the institutions do this already, sometimes unwittingly, sometimes unknowingly, because you can never have perfect storage conditions for each particular object or even the class of objects. So there is always a storage case, there is always a storage or a case that has a set of objects that are not exactly the same, that do not comply perfectly with the environment that is in there. So what we're trying to do is we're trying to rationalize those processes that are already happening. So in this particular project, we want to understand the mechanical response of plastics to changes in relative humidity, temperature, and resulting changes in equilibrium moisture content, and correlate those with, first of all, the type of the polymer that we're looking at, the presence of the plasticizer in the polymer's composition, the amount of plasticizer, and cross-reference those areas to see how those things coincide and correlate. In this specific project, as I said, we're working on cellulose acetate films and polyurethane foams. And I've been mostly talking about the cellulose acetate films because we have almost complete set of data for what we set out to do for this, and then maybe a little bit more about the polyurethane foams if we have time. So how are we going about investigating those issues is we're looking at microscale mechanical testing using DMA, which clearly is a hero of one of the heroes of this meeting so far. And you can see the same photo that Emma showed because we're very proud of this machine and we really like it. And we're looking at primarily TG because obviously you have to do it, and then at the humidity expansion coefficient, also known as the humidity coefficient of expansion is the other way to name it. I don't remember. I'm using this because it's nicer abbreviation, HEC. And then we're trying to correlate that response in macro scale to see the objects that are almost real life size using DIC. So for those who don't know, cellulose acetates are a very widely used, historically very widely used group of polymers. They are cellulose derivative polymers that have been acetylated. There are two main types. The acetate was a little bit older, and then triacetate was developed. The basic difference is just the level of acetylation between them. They've been prevalent mostly in film industry because IPI, of course. But also they have been used in in other areas. So not just film bases and animation cells, but also they were used for molding as toys, kitchen utensils, and things like that. And why we have a problem with them? Because, of course, they are thermoplastic, hygroscopic, and they are prone to self-degradation, so they require specific storage environments. And it's not just that cellulose acetates have those problems. You have other natural derived polymers that do show those responses. So we hopefully will be able to, at least maybe in the future, expand this research a little bit to other polymers of similar classes. So what we've taken as a target or ideal model for what we're trying to investigate are the painted cellulose acetate animation cells. We chose them because they are an interesting object, complex object composite, which are basically this size acetate sheets. Roughly, different film companies use slightly different sizes that are hand-painted with hygroscopic paints mostly. Disney used mostly gamma arabic. We're using gamma arabic because of recipes from Disney archives, but these are usually temperas or gum-based paints. Excuse me. So how are we preparing our samples? We, meaning my colleague Meredith, who's the chemist in our team. So the samples are cast from 20% solution, and they are a mixture of either pure cellulose diacetate or triacetate with addition of up to 20% plasticizer. We are using two historically most popular plasticizers. And each of the diacetate and triacetate mixtures, you can see here the composition. So we have 9 compositions of each, and they depend on the proportion between the acetate and 1 or 2 plasticizers. And then those casts are cut for the DMA. Those are cut into thin strips, 30 millimeters long, 8 millimeters wide. And some of them are painted with historically accurate paint from Disney recipe, from the recipe from Disney Archive. So what are we doing in the DMA? Those procedures for those 2 tests, you can see here, glass transition is a very simple displacement control temperature ramp. The maximum is used for pure acetate. Then for others, we were lowering the maximum down a little bit because we got the samples melting. And the humidity expansion coefficient, so that's a little bit more complicated. What is happening there, we are applying a constant stress to the film in the clamps, stabilizing the temperature at one of those 4 levels, as you see here. And then the sample is being dried at 10% RH and then slowly humidified, allowing for 90 minutes of relaxation at a given RH at each step. And we're doing this either one way in those 5 steps, 20 through 80, or increase and decrease. So we are humidifying and drying the sample without the step of 80%, why I will show you in a second. Glass transition, again, very simple tests. Here you see one of the samples in the film tension clamps. We are taking glass transition from tan delta and from storage modulus derivative. Nothing unusual. And this is how the it is working. And this is how the humidity expansion coefficient curve looks like. So what you're seeing here is the RH. This is the set point. The real RH is never that clean, but the set points makes a nicer graph. So what you see here is the 90-minute period here, and then the strain curve of the sample as it goes through the humidification process. As you can see here, this is why we're avoiding the 80%. You see here that the sample was stabilizing, and then it started softening and deforming plastically. We found out that above 75-ish%, depending on the polymer composition, we're starting to get plastic deformation instead of elastic. So that's where we're dropping the 80% from the two-way tests. Now, how the HEC is calculated is very simple. You take the difference in RH at any given point. We're using the steps that we have chosen. And you take the difference in strain, divide one through another. And what you're getting essentially is a strain cost of increasing your RH by 1 percentage point. And this is how the curve looks for the two-way test. There we go. again, these are two curves of the same polymer, one with paint, one without it. I'll go into those details in a second. So what are the results? In glass transition temperature, it's kind of simple. You can make those nice three-dimensional surface curves, but basically the very simple graph shows that you can see the impact both of the polymer composition and the amount on the type of plasticizer on the response to those tests, which kind of going to be important in a second, because when you're looking at the influence of the humidity of different response to the humidity, so what you're seeing here is the strain. So if you remember the curve, right, these are essentially the points are the strain at the end of each step. So this is fairly simple. Those two are the same. So this is diacetate, this is triacetate. They are at the same scale. So you can see the difference of how those two respond. And you can also see how nicely they sort by the type and amount of plasticizer. The commercial materials that we have bought or acquired behave slightly differently, probably because they have different types of plasticizers in them. But our prepared samples that we know what's in them, you can clearly see how they respond. Now, when you calculate the humidity expansion coefficient, which remember, those are graphs of the rate of change, you can see that, first of all, again, you can see how well the polymers sort themselves by the amount and type of plasticizer. You can also see that the response in the at each step, the response of the triacetate, there we go, it's about a third of what you're getting in the diacetate. And you can also see the nice linear response. So when this line is flat, that means that the strain line is linear. Okay, so that's the polymer composition. Now, what you can also take from this data is obviously how the different temperatures change this response. So what you're seeing here is that 100% acetate, D and triacetate in 4 different temperatures. And as you can see, there is almost no effect until you go to the 70% RH and above. Those are normalized to the dry state, right? That's why we're starting at 0. In diacetate, this is a little bit more wild, but still fairly flat and stable. So it shows that the temperature has rather little effect on this, and the same kind of obviously shows in the humidity expansion coefficient calculations, that what you're getting is very little fluctuations in there when you're comparing one temperature from another between 5 and 20 degrees Celsius. Now, the last factor I promised in the beginning is the presence of paint. And here I'm using the two-way curves because A, I think they make nicer graphs, and B, you've been already trained to look at them, and C, they actually show a very interesting effect. So first of all, you can see how in the beginning, okay, so how to read them, it's basically the curve is strain is going up and then going down. So what you're seeing here is that the presence of paint slows down the initial process of humidification, but then very much speeds up the process of drying to the point where those curves, almost all of them, I think, or if not all of them, actually miss their original 0.0. So when you're applying the humidification and drying at the same pace, at the same rate of change, you get more stress on the drying side than on the humidification side. And this is very well seen in the humidity expansion coefficient graphs, where you can see those peaks at the end here that actually are going higher than the maximum humidification points that we have seen before. Okay, so how does it work out in the DIC, because obviously the objects in real life are not 10 millimeters wide, despite it would make things much easier. And what we're looking at, initially what we've started looking at before we cast our own large sheets of cellulose acetate, we simply grabbed the commercial one, who, as I said, it's supposed to be 100%. It's definitely not 100%, but I guess that's the consumer protection for you. And what we've done with them is we've taken three, this is triacetate, these are diacetate sheets. And you can barely make out, I think here are a large painted cross, a smaller painted cross, and no cross at all. And DIC, for those who don't know, works by taking images of an object that contains an irregular pattern at certain periods of time, and comparing those images, shifts in those irregular patterns allows you to calculate strains. So what we've done is basically subjected those samples to pretty much the same RH fluctuations in our walk-in chamber that has strict environmental controls. We just allowed them to acclimatize and relax more than in the DMA. These have been done every, this is 3 days here. Again, okay. This is 3 days, so we allowed them for 3 days of relaxation at each RH level. The red dots you're seeing are the images that I've taken for analysis. The images were actually taken every 15 minutes, but you don't need that many. You just need those at the critical points. So this was the first part, and then the second part, you can see 12-hour fluctuations with and without constant dew point. So what it showed us is that, first of all, when you look at the images that are scaled to the global maximum and minimum, so the color scales here are the maximum and minimum for the entire test. The left image is an the axis strain, the right image is the y-axis strain. So what you can see here is kind of the same situation that you have seen. This is an example that contains small cross that covers 8% of the surface area of the sample, number taken from one of the animation cells that we've seen. And what you see here is that at the end, the sample has not returned. It has curled more after drying than when it was relaxing during humidification. Again, we don't, I don't remember this. The numbers are in the ballpark of the strain rates we've seen in the DMA. They don't match ideally, but we're gonna get there. What is more interesting, though, is that if you look at the local, when you scale those images to the local maximum and minimum for each particular image, you can actually start investigating how the influence of this local cross here is acting, and how the paint actually does expand more. So it does correlate with what we've been doing. And finally is with the 12-hour shifts, what you can see here is that paradoxically changing the dew point caused less strain, which was surprising to see. We definitely have to investigate this further. But it definitely shows you that there is potential in this observation. And we're looking at this technique primarily because, courtesy of British Film Institute, we do have animation cells that are coming from an end of an animation. Animation cells are great because there is a lot of them, and almost every country has some. And we have animation cells that basically have a cross like that. So we're going to, after we finally set a procedure for this technique, this was just a proof of concept, but when we finalize the technique, the procedure for this technique, we are going to use the historical objects, and we are going to investigate those changes on actual aged animation cells. So as I said, we are working on the foams. We did manage to extract some data from the polyurethane foams. I cannot tell you what they mean just yet, but again, this is coming. And we definitely will have to adjust the procedure for the humidity expansion coefficient because 0.01 megapascal, by the way, correct the typo in your abstract booklets, is definitely too much. And you can see that this, the foam does want to swell, but then it's getting crushed by the test. So to conclude, we have definitely found out some relationships between the material composition and the RH response. We found out about the differences between diacetate and triacetate response. We know that type and amount of plasticization can affect that moisture response. There is very little effect of the cellulose acetates. However, when you look at the TG curves, modulus curves in the TG tests at the space between -20 and +25 degrees Celsius, there is about 20% drop. So we will definitely have to look into that. How safe is that change? And then presence of gamma arabic-based paint is definitely increasing that response. We see that in microscale, and we see it specifically at the edge of the scale. And definitely there is a difference between humidification and drying. CTA hopefully shows us some linear behavior, which is great because hopefully if we make this model reliable, what the repeatability of the data gives us, we hope that this will show that there are certain areas where you can allow for very predictable behavior. And depending on your object, you will be able to monitor it and allow it safely to work with the environment. Thank you.
Thank you very much, Jacek. And I would like to open the floor for the questions.
Okay, wait, better. Thank you, Jacek, for your presentation. I have two questions. What do you think? Do you think your films have hysteresis of absorption when you see your two steps absorption curves? Do you? You didn't mention it, but can you comment on that absorption of like hysteresis of absorption? Of your moisture content? And second question is, I would like you to have your insight on maybe the mechanosorption of your material, because when I see your increase of strain with humidity, I wonder if you think you have this kind of also phenomenon that you often found in actually hygroscopic materials.
So the answer is probably yes to both. We haven't dived into the numbers that deep as of yet. There is definitely hysteresis in the RH response. You can see that sometimes, that especially when you look at this data. Here, right? So when you look at the drying part, because we store the samples at 50 degrees Celsius, we have them in a lab that is very well conditioned. However, just the time to prepare the test, you're transferring the sample, the machine just throws a hiss and starts to do something else, and it takes like 20 minutes more to start the test. You already see that difference. So I'm for example, not very well, I'm not wedded to this data at the very beginning. Definitely, that's why I normalize everything to the 10%, because I'm much more confident. So there is definitely response, especially in CDA. You absolutely see that. What are the amounts? I have not calculated. With the mechanical response, probably the same, especially like in the higher humidity when you start seeing plastification effects of the moisture present. Definitely yes, but that again that will definitely require more calculations in there. Thank you.
All right, thank you. Yeah, I see. Emanuela.
Hi, thank you for your presentation. Can you go to the next slide in which you show the strain? So I have a question. When you plot the hygroscopic strain, the one at the left in which you have some irreversible shrinkage, so did you repeat this cycle just once or you tried to do it again? So I was curious to know whether the irreversible shrinkage occurs the first time and then you have a reversible behavior, or if you would do a cycle again, you would have additional irreversible shrinkage.
So we haven't done more than one cycle as of now. So this is coming, but we haven't done this yet. Every sample we have done, we have cycled once. You can, so you can see in the CDA there is a little bit of shrinkage here, but it's very minuscule. In CTA there is almost no shrinkage upon return, but we don't know how this will be affected if you repeat it twice. That we haven't found out yet.
The reason I'm asking is because it reminds me the behavior of a printing paper in which you have some sort of behavior like that. So the first time that you have a cycle of moisture, you have the release of the reversible shrinkage, and then you have a reversible behavior. And it depends on the way the samples are dried. So if there is some dried in strain that is released the first time or not. So maybe there is some analogy in the behavior of at least the mechanical conditions. Just a comment, maybe you can think about that when you will analyze the data.
Yeah, no, absolutely. And I have worked with viscoelastic polymers before, and we had that situation. So you had those loops basically changing every time and not getting as aggressive after some time. So we hope to find this out. Obviously, one cycle is not relevant for any kind of like modeling. I mean, it is relevant, but it's not set in stone for making any kind of future predictions. You need several cycles, that's for sure. That's why we're hoping more for the DIC in this one, because we can do much more and we can leave those tests for longer. Here we are limited by the supply of nitrogen and other things, so we only can do probably 3-4 cycles like that before we would have to change the tank, and that would break the test. So there isn't much we can do about that. But yes, it will come.
Thank you, Jacek. So I have 2 questions. One actually is about this slide. I was wondering, since you're comparing no paint and paint, did you observe some damages on your paint? Of course, you did only one cycle, but is it one thing you would like to investigate to know how much this swelling and dimensional change would affect the paint layer? And the second one is like, the way those acetate sheets are made, if I remember well, well, in the industry they have this sort of tumbles. So the way of making those films has a huge influence on their properties. How do you think this will affect or change the result that you obtain on your casted films?
So this is something I don't have a slide for, but we have done. So the commercial one that we bought, so I'm going to answer the second question first. We have done a test where we basically took a single sheet of commercially bought acetate, and we took at 4 angles, so 45, 45, 90, and 180 along the x-axis. So we have done this. There is a difference in response because they are technically cast, but in reality they are drawn through the manufacturing process. So there is a difference in response there. Our samples will not be drawn, so that is obviously a limitation. But it also gives us a chance to actually do whatever we want in terms of cutting them, because it's labor intensive, especially for my colleague who needs to prepare them. So we went for this, and also because we don't have a production line set up. And the previous one was about this, whether we see the damage in paint. No, and I haven't seen any, at least not something that I could see in normal magnification. The problem is that the paints basically stick to the clamps, So when you can only observe it in the clamps in a natural state, let's call it. So when you try to remove them, I make damage, basically, when removing the sample from the clamps. The paint is basically very delicate. So the only way I can see this is whatever magnification I can get after the test ends and before I remove it. After that, it's just not valid.
And I guess the paint is very new as well, right? So it's fresh and hasn't aged.
Even if I leave it, basically the glue migrates from underneath and sticks to the clamps. So when I try to remove it, I always create a damage in the paint layer.
If we don't have any more questions, let's thank Jacek again.